Hello and welcome to this KNX Secure Webinar. My name is Christophe Partoens, so I'm the presenter of this webinar. And so here is the agenda. So 3 topics actually, one, well, very short, just to explain you the base for KNX Secure that is used. 2, KNX Data Secure, and 3, KNX IP Secure. So the base for KNX Secure is AES, which is the abbreviation for Advanced Encryption Standard. So it is actually a standard, another standard that we just took over in our standard, so to say, or that we will use in our products in order to assure data secure and IP secure. As such, in case you would like to have more background information, well, obviously you should Google it or just go to Wikipedia, because you will then find, of course, more information, because the topic AES as such is beyond the scope of this webinar. However, I want to point out that some algorithms, some nice animations on the algorithms can be found via this link here. So it's a YouTube link, and well, I can certainly recommend it in case you would like to have more background information. Okay. Then, as such, second topic, KNX Data Secure. And before I really go into the KNX Data Secure in details, I want to compare it first with KNX IP Secure, because there's definitely a difference there. Well, in the sense of encryption. In KNX Data Secure, in that case, only a part of the telegram will be encrypted. It's the APCI, so the application programmer or application protocol control information, sorry. So the application protocol control information, yes. So it's actually an identifier for a service like memory write, memory read, group value write, group value read. So all these services have an identifier and some useful data, or also called payload, and actually only those 2 fields of the telegram will be encrypted. However, the non-encrypted fields will be used as input for the encryption of APCI and payload. And obviously, well, data secure as such can be used on any KNX medium, so twisted pair, power line, radio frequency, and also IP. But for IP we have a specific secure technology which we call indeed KNX IP Secure, and the biggest difference is that in this case, so for IP Secure, the entire frame will be encrypted, and of course this can only be used on IP. So there's definitely a difference there. Okay, let's have a look at the details of Data Secure then. So first of all, comparing it with, let's say, a plain device, so a device that has no security, no security technology on board. Well, in that case we say that, well, in this context, comparing it with a secure device, that such a device has a plain stack, where the layer 7 actually only exists out of the application layer, or is the application layer. Now, in case of a secure stack, so a secure device, we see that the layer 7 will be split up into a plain application layer and a secure application layer. So that means some extra and internal parameters in order to define frame security will be used. With internal, I mean these are parameters that will not be visible on the bus. What are these extra parameters then? Well, there's a parameter for authentication, for confidentiality, and also there is a security link table index that will be used. And of course, graphically I can explain it as follows. So indeed the secure application layer will be put in between the plain application layer and the transport layer. So that's actually the modification that has been made in the context of the OSI communication model. Okay, So, well, about that security link table, so an index there or an entry there can either be a point-to-point, can be used for point-to-point communication. In case of point-to-point, the security link table entry is a mapping between an individual address and an encryption key. In case the entry in the security link table is used for multicast, in that case, this entry, this security link table entry, is a mapping between a group address and an encryption key. So this is actually, these are the two possibilities. Then the frame as such, well, looks as follows. So we see indeed well, it is specified from the APCI onwards, because it's that part that is encrypted, right? The rest is not encrypted. So we start the definition from APCI onwards, so the application protocol control information. Here what we see is that there will be a fixed code there, which we call, or fixed APCI, fixed identifier, which we call APCI sec, APCI secure, of course. And yeah, so that's the first field. Second field is called the security control field. 8 bits are defined there, for which the first one, the most significant one, is actually to indicate whether the frame comes from a tool or not. If it comes from a tool, the bit will be set, and it means that that it is not linked to a specific individual address. Next 3 bits are called SAI, abbreviation for Security Algorithm Identifier. It's just to indicate whether the frame requires authentication only or a combination of authentication and confidentiality. SBC, next bit, is to indicate, so it's a system broadcast flag. It means, well, if this bit is set, that in case there is a media coupler used in the installation, that the telegram will also propagate into the other medium, so to say. So from TP to RF example given, if this bit is not set, well, then it will just then the frame will not be copied into the other medium. Next 3 bits is for the service. So there are 2 services defined. That is either the data service or the synchronization service, request or response. Next field is the sequence number. Sequence number is has a length of 6 octets. Which means, if we make a calculation, that it will overlap every 10,000 years approximately. The sequence number is there to protect against the installation against replay attacks. So indeed, if a receiver receives 2 telegrams in a row with the same sequence number, then the second one shall be discarded. So that's the protection actually. Yeah, okay, so that's the sequence number. Then still about the sequence number, of course, it could be that if a device gets deconnected from the installation for whatever reason, so that it loses indeed the sequence number from the communication partner, then well, then if there would not be some synchronization service, then no communication. Well, communication would only be possible to start up from scratch again. I mean, then for both devices, which is of course not the intention. So therefore, the synchronization service, in order to in order to provide a mechanism in order to restore such a situation. So there will be a read and response between the 2 devices. The read and response messages then as such are also encrypted, of course, and there's even a challenge code used here in order to make it even even more secure, so to say. So even the synchronization service is secured here and is there, as I said, in order to restore a situation where one of the communication partners lost the sequence number, so that communication can go on after, example given, reset of the device or reset of one of the communication partners. Next field in the KNX Data Secure Telegram is an empty field. Actually, it's just there to shift the bit position for the plain service. So it's just to make sure that it will start at the same bit position. So the actual payload then, so that's what we see here. So the payload is encrypted in case of confidentiality. In case confidentiality is not requested, well, then the payload is not encrypted. But if it is encrypted, then it will be, then the calculation for this encryption will be based on AES, which we see here illustrated in the slide as well. Well, first of all, the encryption will take, there's input 1, so to say, so information from the plain service will be used. And also the other input is required here, so the secret key, that is which is stored via ETS into this device, and this will then indeed render the encrypted payload. And there's also a 4-octet message authentication code, and also here this authentication code is based on AES, but it is a different let's say algorithm than the one that is used for the payload encryption. Also here information from the plain frame will be used as input together with the same secret key that was used for the encryption of the payload, so the same secret key that has been stored into the device via ETS. Okay, data secure in practice then. So here we see the situation where so we see here the ETS professional software, installed on laptop. Here's a KNX device, a KNX secure device, and an interface, a USB interface. So what does it mean for the installer in practice to secure a KNX device? Well, to set up security, so to say. Well, first of all, what should happen is to set up the so-called FDSK, the factory default setup key. So this is the initial key. So typically it's an so ex-factory the device will be delivered with a QR code, right? So that means this FDSK needs to be entered in the ETS project for this specific device. This operation happens entirely outside the bus. So this FDSK will never be communicated over the bus. So it happens entirely outside the bus. Then from that moment onwards, the device, the ETS will be able to indeed communicate with the device, and it will do that via the so-called tool key. The tool key, which is actually encrypted with this FDSK, will allow communication with the KNX device. So will allow communication between ETS Professional and the KNX device. Once this is done, you should of course take care of this FDSK as K, so the factory default setup key, so to make sure it's put somewhere in a safe place, so that it has no, so that no one else has access to it. Okay, and then from that moment onwards, there's actually, so to say, a secure link between ETS Professional and this device. But this is of course only the management part. Now we also need to secure the the runtime part, so to say. So that's the next step, that is to create the runtime keys indeed. So example given, let's say the device has 3 communication objects, all 3 shall be secured. Well, then you need to program this via ETS. So let's say a runtime key per communication object, and now this device is also secured on runtime. So this is how it will work in practice. Okay, permissions and roles, better said. Well, if we look at KNX Data Secure, then what we see is actually a a gate at link level. For multicast, it means that this gate will open for any entry in the security link table with a matching combination of, a matching individual address plus group address combination. In case of point-to-point, the gate will open for any entry in the security link table with a matching individual address, right? And this could be a problem because there could be some conflict of interest, as we can call it. Here I try to explain it with an example maybe. So here we see the system integrator, and we see here the building manager. So and they want to have access to the same device, however in a different role. So here's the device, the KNX Secure device, which has a group address table and which has a building entrance permissions settings. The system integrator typically is of course interested in the group address table, and the building manager is interested in this in these entrance permissions. However, the system integrator shall not have access to the entrance permissions, and also the other way around, the building manager shall not interfere with the actual functionality of the device, so with the address table. So we see different roles, we see conflicts of interest, so to say. How to solve this situation? Well, that is by means of permissions and roles. So instead of having one general gate, so to say, at link level, we will make it more. We will add a concept that we call permissions and roles in order to fine-tune this link, so to say. So an example is as follows. So we see here, example given, we see here data and services represented by these symbols here, these cylinders, and with a red gate example given, we only have access to this specific part and to this specific part of the data and the services, and with a blue gate we only have access to the blue specific part, and with green yet another gate is defined. So that is actually the global overview of what we try to do with permissions and roles actually. Now an example maybe a bit more concrete. So data permissions could look as follows. So let's say that there is indeed, if we look at the group objects, then we have 3 in total, so 1, 2 and 3. Well, then the data permissions could be set up as follows. So a 4-bit code indicating read-write, authentication and confidentiality. So in case of the red gate, well, then we want this combination, right? For blue we want to have this combination, and for green we want to have this combination. So you can really define the different roles and link that to the specific resources, the specific data, or the specific services that are on board of the device. In case of services, the table could look as follows. So service 1, service 3, service 1, service 2, service 3. Here only a 2-bit code is required in order to set up the service permissions, so authentication and confidentiality. So in case of red, that means, so here in this example, that for all 3 services, authentication and confidentiality is required in order to have access to the service. Otherwise, no access. It is just an example. Also, security whitelists and blacklists are defined. So with a whitelist, we actually set up or indicate which services shall always be accessible via plain communication. The typical example could be indeed the manufacturer code. Some services and some data shall never be accessible via plain communication. Then, okay, we need to put this in the blacklist. Like, well, typical example, indeed, security interface object properties. That is obvious that you should not put those, or not make them accessible via plain communication. Otherwise, the device by definition is not secure. Then there's also the intermediate list. It's also possible that, well, there are services that in specific context need to be accessible via plain communication, and then in a specific context not anymore. A typical example is indeed the restart service. The restart service is definitely required for plain communication, let's say during. So the restart service should definitely be accessible for plain communication during the configuration of the device, but then not afterwards anymore. So once it is configured, you can only have, example given, access to the restart service if there's authentication and confidentiality. So that is indeed an intermediate. We call that an intermediate list of services and data. Okay. Then KNX IP Secure. So here we see an overview of the different services that are defined. So the secure wrapper, the session request, the session response, session authenticate, session status, and timer notify. Well, okay, anyway, in general we can say that the entire standard KNX Net IP header remains unchanged because of, well, so we didn't change that for KNX IP Secure. So even the protocol version, which was set to 10 hexadecimal, has been maintained. That means, as such, this is a future-proof concept. So that actually means that it is backwards compatible. So it's not because of IP Secure that the old, let's say the older devices, the previous generation, that we cannot use them anymore. That is actually what it means. Okay, anyway, the payload encryption, in case confidentiality is requested, then this algorithm will be used. So it is an algorithm based on where the encryption is based on, or the calculation for the encryption is based on AES. Where also here information from the plain frame will be used as input together with the secret key that was stored into the device via ETS. Also in the IP Secure frame there is an MAC field which is also based, well, for which the calculation of the encryption is also based on AES. However, also here a different algorithm will be used than the algorithm that has been used for the encryption of the payload. And also here information from the plain frame will be used as input for the calculation or for the encryption, together with the secret key that has been stored into the device via ETS. The secure wrapper frame can be used for both IP multicast communication as for IP unicast communication. In case of multicast communication, an encryption key will be used. In that case it means that one key for an entire KNX.IP multicast group will be used. This is a key that never expires. Of course, when the key gets compromised, you shall, of course, set up a new one for the entire group, right? But as such, as long as it's not compromised, it will always be the same encryption key. In the case of multicast communication. Multicast communication, well, there is a specific, let's say, defending mechanism implemented, so and defending a defense against replay attacks, and that is by using a shared timer. A shared timer which is added to each frame, so each sender puts that timer in the frame and then sends it out. If a receiver discovers that this shared timer, so that the timer that was put by the sender in the frame is not valid anymore, so is too old, so is outdated, that's actually the word, then the receiver shall discard this frame. Well, of course, it can happen that a device loses the synchronization, so to say, loses the timer. Well, in that case, there is a timer synchronization mechanism foreseen, so the device just needs to send out a timer notify, and then other devices will react to that by sending yet another timer notify. After receiving this timer notify, the device that was that lost the timer should use then indeed the new timer and can communicate again in the context of multicast communication. Okay, multicast. Now unicast. Well, unicast is a bit different because here we need indeed a secure session for tunneling and for device management. So it's a bit more, it's a bit stricter, let's say, a bit more complicated also, because here for confidentiality encryption will be used, and for data integrity message authentication code. But everything will be based on a session key, and that is the most important difference, because the session key is really each time a new key per communication session. So whenever two IP devices want to communicate with one another, they each time need to set up a new session key when they want to communicate with one another. The session key is negotiated via the so-called ECDH, which is actually a specific technology in order to authenticate the two devices, so the two communication partners, against each other. The ECDH technology as such, or concept, is also at the same time a protection against the man-in-the-middle attack, because indeed the devices authenticate to each other. So the device to the client, example given, and the client to the device. So the client, by client I mean the ETS, or in other words, when ETS wants to communicate via Unicast to a specific IP device, then ETS first, the device first needs to authenticate itself to ETS, and then ETS needs to do the same to the device, right? And that gives indeed that's the protection that as such, this concept is a protection against the man-in-the-middle attack. Okay, yeah, that's how I should put it. Okay, anyway, The Unicast Communication as such is also a really strong protection against offline dictionary attacks. So against, so it is a protection for passwords. That's actually what it means. Such online attacks are possible, but of course hackers don't really like this, because doing these kinds of attacks online means exposure time, and that's what a hacker doesn't like, of course. Okay, there's also a defense against replay attacks. So a counter is used in this case, so not a timer, but a 6-octet counter, and of course always the same principle applies is when a receiver receives the frame with the same counter, well, then the second one shall be discarded. Okay, the Unicast Communication, so the principle behind it, so there is always a common session key, so both devices that want to communicate with one another will use the same session key, and they will mutually authenticate to one another, and this will be done based on the Diffie-Hellman concept. That means this key, this common key that they want to check whether they indeed use the same session key, well, this session key will never be exchanged. So it's a specific concept that is used, a specific technology that is used, and that will allow to indeed authenticate the devices to one another. Yeah. So that means indeed it starts by exchanging public variables, so from device A to B and from B to A, and when both find out, okay, we indeed use the same session key, we can start the session and we can start the service. So that is actually the idea behind it. Here I added a few slides with a very simple example where these variables are exchanged, and which will allow you to well understand this Diffie-Hellman principle. So here we see this from A to B, how this is checked, and then from B to A, and also here how this is checked. So you can, well, after the session here, after the webinar, I will send you these slides, because of course I have your email addresses, and if you are really interested in this concept, you can check these slides for yourself. So okay, as such, that was actually the last slide that I wanted to present to you. So actually done talking now. For the rest, what I can say is that well, I can conclude the webinar now. There are still some follow-up webinars that we can recommend, but as such the webinar is now finished. And before I conclude the webinar, I want to still present a few extra slides, and while doing that I want to thank you for being here. I want to thank you for your attention, for considering KNX, and maybe we see one another in one of my future webinars. So thanks again, and goodbye.